In this question, we've got an unidentified compound which we've been told consists of carbon, hydrogen, and oxygen. And we've been asked to work out the empirical formula of this compound. Okay, so one of the first things I'm going to do looking at this is I'm going to just do a quick check, and I'm going to add up the percentage abundances by mass, which are effectively given in the question, right? So if we do that, we get 6.67 plus, well, let's put the 40 in first, all right? So 40 plus 6.67 plus 53.33, right? And when we when you add that up, what do you get, right? So in this case, you actually get 100, right? When you add these up. And for the purpose of solving this problem, one of the things I'm going to do at this stage is I'm going to make an assumption, which is I'm going to assume that the sample of the compound that I'm working with is a total of 100 grams, right? This is going to enable me to convert these percentage abundances within the compound by mass into masses, right? In grams, and that's going to help me get to figuring out the empirical formula. So if we do that, we effectively get 40 grams. That's a bit too. 40 grams. That's for carbon. So carbon is 40 grams. Hydrogen, 6.67 grams. Oxygen, 53.33 grams. Okay. And what am I going to use to try and progress this towards comparing the actual amounts? Because I need to compare the atoms. How frequently does each atom occur per element? I need to be able to compare those, and that's more of an amount of substance comparison. So I'm going to need to convert this in this case to moles, right? So as we would know, the equation which shows a relationship between masses as we have and moles would be that the moles, N, is equal to the mass divided by the molar mass, which is mR, right? That's in grams, and that's in grams per mole. Okay. Now we need to effectively get the molar masses in order to actually use that equation on these values we have. So let's do that. Let's you may be aware of what the molar masses for these are already, or given how common these elements are, but let's refer to the periodic table nonetheless. So if we do refer to the periodic table, we've got here carbon, hydrogen, and oxygen. We've got, so for carbon it's going to be 12, for hydrogen it's going to be 1, and oxygen is going to be 16, right? And so if we integrate these and we say, okay, so when we're looking at the moles, N, right, we're actually looking at 40 divided by 12. We're looking at hydrogen, we're looking at 6.67 divided by 1. We're looking at when we're looking at oxygen, it's 53.33 divided by 16, right? And so at this stage, I would invite you to have a go, and if you work this out to see what numbers you get out of this, right? And at this stage, we're going to represent it now as a ratio between them. So for carbon, when you do that, you should get, and I'm going to represent this particular one to 5 decimal places. So I'm going to get 3.333. For hydrogen, we are dividing 6.67 by 1, so realistically we don't need a calculator to work this out, right? So that is literally just going to be 6.67, and then we compare it with the final one, the oxygen, 53.33 divided by 16. So if you do have a go at calculating that, you should get, and again for this one I'm actually going to represent it to 5 decimal places. 3.33313. Okay, so we're looking for the empirical formula. We're looking for the smallest or the simplest whole number ratio, right? We don't have that at the moment. We've got these numbers which are, not only are they not integers, they don't exactly seamlessly round to integers. They're not super close to integers in any case, right? So what I'm going to do at this stage is I'm going to divide all of the numbers by the smallest one, right? And in this particular case, the smallest one we have is 3.33313, which is for oxygen, right? So we're going to divide all of the values by that. So let's do that. Divide that by and so if we run those calculations, what do we get? Well, in the case of carbon, you're going to get effectively 1.00006. In the case of hydrogen, you get 2.00112, and in the case of oxygen, well, you're dividing the 3.33313 by effectively by itself, and so of course you don't need a calculator to kind of figure out that that's simply going to be 1. Okay, now have we made any progress since running that last calculation? Are our values closer to a simple whole number ratio? Well, in this case, the answer is yes. We are much closer to having a simple whole number ratio. In fact, when we look at these numbers that we now have, this number to 2 decimal places is an integer. This number to 2 decimal places is an integer, and of course this is an integer already, right? So therefore, at this stage, all we actually need to do is round these two values, because they're so close to being an integer. We can just round them. So if we round them to round everything to 2 decimal places, we get 1 to 2. That should be up. Yeah. And 1, right? And of course this just simply is 1 to 2 to 1, right? And so as we remember from above, this is carbon, hydrogen, oxygen. And so effectively, do we now have our simplest whole number ratio? Well, yes, I would say at this stage we can confidently assert that this is actually our simplest whole number ratio, 1 to 2 to 1. And therefore, right, this would effectively mean that attributable to the carbon is a 1, to the hydrogen is a 2, to the oxygen is a 1, right? And of course in our formula, if there is a 1, we're not going to actually write that, are we? So this is literally just becomes CH2O, right? And that is our empirical formula.